Previously, we've seen how to fix sliding issues with our foot, but we had to know when the contact were happening. Now, we might want to do this automatically, and this is the purpose of this paper. Hi, I'm Jerome, and today we'll be looking at knowing when to put your foot down, a paper from 2006. This paper would basically use a model that you train on a few animation examples, and then it will try to extrapolate on all the animation data you have. So for this, what I would do is that I will first load my character, of course. I have a few constants that I will need later. And finally, what I will do is that I will load a bunch of animations, and I have different walking style coming from different actors. I have running animation, I get the dance animation, I get aiming animations. So quite a lot of different type of animations. So I have different type of foot contacts that I will be able to learn in the system. So I get runnings, I get walking backwards, I get a bunch of dance animations right in the middle there. A lot of different types of animations that we will be able to learn from. And if I look at how much data I have loaded this time, I have 22,600 frames of animations that I would want to use to learn what foot contacts look like. So how this paper works, basically the idea is to train what they call an oracle that is able to look at your foot contact or foot animations and tell you if it's contact with the toe, heel, for the left toe, left heel, or right toe, right heel. So what we will build first is the feature vector that represents the data that we will feed to the system to learn from. And it's not just the entire animations we give him. We will just give a feature vector that has the position of the toe, heel, and knee of both legs, but not only for the specific frames, but also for the frames, for an entire windows of frames before and after. So you basically look at a big windows of frames with the trajectories of all those positions for the heel, toe, and knee. And that's allow you to predict if at frames right in the middle, if it's a contact or not. So that's the feature vectors that we're trying to build. What they had as window, what they said they were using a 10 frames windows before and after, but the paper is actually running at 60 frames per second. I'm only at 30 frames, so my windows will only be 5 frames before and 5 frames after. And what we will create is this. I will compute it for the entire animation at once, so I don't have to recompute that every time I need to compute the feature vectors. So I will compute it once. So I get all my animations, all my frames. Then I get my 6 bones I want to use. I get the X, Y, Z positions in space of my 6 bones. And I do it for the entire windows of frames, so for my frames and for the 5 frames before and the 5 frames after. That gives me my feature vectors here. And I have a second one, which is the feature vector indices. Basically, it will allow me to find back from my feature vectors which frame animations it corresponds to, because I will have all my animations into one big feature vectors, but it's actually a bunch of different animations with different timing in it. So I need to be able to trace that back. And basically what this says is that the positions and orientations is irrelevant to know if you have a contact or not. So what we want to do is to make sure that every feature vectors is basically realigned in 0, 0. So it all looks the same. We really look at the trajectory of the foot itself and not where it was in space. So what I will do for this is that I will project my hips on the ground to use it as the root motion, let's say, and I will compute the position of the foot for the entire windows of frame at that specific position in space. So probably easier to show and to explain what I was doing here. So I compute all my feature vectors, and now basically the feature vector is this. You get all those little arrows, little dot. So here we are. And so if I take this, for instance, it's one feature for one specific frames. So, and you get, so you could actually see the motions itself. So it's all stable, but that's the feature vector that the oracle will see, right? And so now that we have the feature vectors, we could start to try to do the training. And to do the training, what would happen is that we will use a k-nearest neighbor classifier to classify all those feature vectors and give them a label. But we'll have to do the training by hand first. And what they do is that they go for a 200 frames sequence at once. So they slice the entire animations, a bunch of clips, and you do the training on one clip, and we will iterate with that kind of stuff. So what I will do is the same thing here. I will start to train my oracle. So I have my trained feature vectors, and I will have my trained label that tells me if I have contacts or not. And at this point, they're just empty because I haven't trained anything. And I will start to manually train one clip. And the thing I will do, so I'll execute this. I will pick basically the first clip inside of animation. So I take the 200 first frames of animations in my entire system because I don't have anything better to start from. So let's start with the beginning. And so now that I would have this big code here, which actually is just there to let me see the data I'm looking at and the contacts I have. So this is the piece of animations, and I will start to train. So that's the piece of animation that we start to train manually for him to learn from. And basically, because I have nothing at this point, you can see I get no contact. But if I come here and I start to click, I will actually have the representations of the contact that's happened here, and I could do it for both heel. So you could see it turns green when I say that this is a contact. I will not do it entirely manually at the first step because that would be really annoying to go through all of this. So what I would do is that I would generate using speed, as we were doing in the other papers before, but I will use bigger range, and then I can start to tweak my data as long as I decide that this is still a contact. So foot contact, that's fairly good. And I will probably, so here I have a bug. And so I will start to tweak this manually for each of my animations, make sure that it is correct most of the time. And I will probably speed this up so you don't see me going insane doing this by hand. So I see you when this is done. And now basically I have tweaked by hand all my contacts. So I'm making sure that they looks like what I want them to be. And so I have one piece, I have one clip that I've done manually, and I can start to train my oracle with what I've done so far. So what I would do is I would take the trained feature vector, and I will concatenate what I already trained with the new clips I've just done. So this is just to grow slowly what data I've actually trained. So my trained vector is just growing with my label, which means now that I actually have my trained feature vectors, and I will be able to start to use the k-nearest neighbor classifier. What they do with the k-nearest neighbor classifier is basically feed all the features they've trained and all the label into it, and then we will use it to predict in the futures. But to win some time, we will not only give the trained feature vectors, we will also give the mirrored version, because everything we've done on one side is actually applicable for mirrored animations. So what I will do is that I will mirror the trained feature vectors just by multiplying the x values, because basically I've made sure that everything is aligned around the 0, 0s and the orientation. So I can just mirror the feature vectors and I can mirror the label, which is what I'm doing here. So the classifier itself will have a much bigger trained feature vectors, because it will have everything that I have done plus everything mirrored. And I can fit this into a nearest neighbor class from SciPy, because luckily enough, it's already written for us, and it is extremely fast as long as you just use the default Euler distance matrix. So we will use that one because it gives us a really big boost in performance, and it's really easy to do. In the paper, they were using also the nearest neighbor, but they were doing it themselves in a brute force manner. And they used the Euler distance anyway. So we could just use what exists for us and use the speed as much as we have. So we've trained a classifier with the nearest neighbor with a number of neighbors equal to 10, which is again the values they were using. So what it will give you is, as soon as you're trying to ask for a position inside of a feature vectors, it will return the 10 closest one, which is what we're interested in. And then we've trained the nearest neighbor. Now the oracle can start to do predictions, so we do need to be able to predict. And how the predicts were, what is, yes, it's here, classifier. And so how do you predict if a specific features is a foot contact or not? Basically, what we do is that we take the 10 nearest label to the one we have, and then we sum them and we divide by the total. So it's just a probability that the classifier gives us compared to everything else it has seen. So if you have a probability over 60%, we would say that it is a contact. If we have a probability that is less than 40%, it is not a contact. And if the probability we find is between 40% and 60%, we basically switch only depending on the previous frame. So if we say I'm in 0.5 and the previous frame says I was in contact, I'm still in contact. If I'm 0.5 and the previous frame said I was not in contact, I'm not in contact either. So it's just to avoid jittering values, that if you're always between 0.5, 0.5, that kind of stuff, is to avoid to have on, off, on, off, on, off. It's just we smooth the signal by saying only when we were sure it was on. If you're unsure, we're still on, and then as soon as we're sure it's not, we're not. So this is what the predict function will do. We give him a feature. Well, it's multidimensional inside of SciPy, so the features itself could be only one specific frame, but it's more interestingly, it could be an entire animation, and it will tell you the label for the entire animations this way. So this is what I do, compute the probabilities. So I'm asking the classifier for the 10 nearest indices, then find the values inside of those labels, divide by 10, and then check if it's less or more, and if it's in between, I make sure that it follows the rules. So that returns a label. Now I have the neighbors. The oracle is able to predict, but how well will it predict? It will probably be really bad, because we already trained it on really small data. So the idea now is to iterate through the training process as long as you need. And the idea to do this is basically what they've done, I guess. So they talk it about the important sampling. So that's here. So what you will do now is that we have a training system. What I could do is I could ask the classifier to actually look into all my animations and tell me which frame has the worst possible distance between all my features. So basically, the k-nearest neighbor will have a bunch of features that will be in space around here, and all my animations will be around there also. But I might have animations that will be really far, for which I haven't trained anything. And I ask him to find me the frame of animation that is the furthest away from anything he has seen already. And when I have that frame, I find the clip around that one that I have to train, and I will start to do the training on that one. So I make sure that I will start to train the system to see the most different animations possible. So this is what this will give me. So basically, I'm requesting all the distance with my indices, and I'm asking to find me the worst one, and that becomes my new animations I would start to train, and that I get back the animations I want. So I run this, it gives me a new feature vectors, and I can see what it has done. You see that it started already to predict a bunch of stuff, and it probably guessed quite wrong on a lot of stuff, right? It could detect that sometimes there was contact, but then, so it detect that left leg fairly good, but then it's still in contact. So pretty bad at when you only train a riddle system. So basically what we have to do now is manually correct this clip, and then when this one will be corrected, we could again concatenate with what we already trained, and then we can retrain a new classifier, and we keep iterating this way. To avoid doing that with you, what I've done is that I've already went through that process several times, and I can just reload this data. So basically what I've done is that I've trained 10 different clips. So out of my 22,000 frames, I've trained 2,000 frames. And I can actually train my classifier with these values. And if I try to see what was the worst possible animations it could find, this is the first thing. So this is the one that it will say is the worst animations and predictions possible. And we could see that it's not too bad at what it predicted. So the idea of this paper is just to stop as soon as when it tells you that the worst frame is this one and it's actually not wrong, you could assume that you've finished training basically with all the animation of data you have. So this is how this paper works. It's fairly efficient, I would say. It's the first step into that machine learning concept, because basically it's a classifier, it's a model that you train, you fit data, and you predict. It's the basics of all machine learning systems. So it was an interesting introductions on all of the systems. I haven't talked about k-neighbors and how they work and all that kind of stuff. You could find a lot of videos about the system themselves and those libraries themselves if you want to. I hope you liked it, and see you next time.